Tapia Carmen, and this is my Physics 2211 Lab for Oscillations. Alright, the content of this lab include purpose, physics, code, error, and then any questions that may arise. For purpose, the purpose of this lab is to be able to observe the conservation of energy via a computational model versus an experimental one. The lab was conducted via spring with a mass attached to it. All right, physics principles. These are the common ones. We know the net force acting on the spring is negative mg, and then the spring is pulling it up. So it'd be this. Eventually, L hat makes it positive, even though there's a negative here. And then you need to know your velocity update formula, your position update formula, your period formula to find k. So from the video, we can see that 3 oscillations takes approximately 4.571 seconds. So you plug all those values in and solve for k, and you get k is approximately 6.83 Newton meters. And then for L, you just plug in the same thing. You solve for L naught, and then you get that L naught is approximately 0.123 meters. All right, this is my video for the actual experiment. All right, that's enough. So these values, then I put them into a file, an Excel file, so I could upload them to my actual code that you'll see later on. This is the link to my actual code. All right, so let's start for the code. The position vector was found by just using our tracker information. G is 9.8 from default by default. The constant of the spring we solved beforehand. L naught we solved beforehand as well. L is just the ball dot position minus spring dot position. L hat, I wrote it out, and then S is just the L minus L naught, the magnitude, like the absolute value basically. And then for kinetic energy, we just do 1/2 mv squared, and then gravitational potential energy we do mgh basically. This should be ball dot position dot y. And then for the spring potential energy, it's just 1/2 s or k s squared. And then for total energy, it's all of those added up. This is more code. We just define everything, and then we calculate our actual spring potential energy right here, or spring force, I mean, and then gravitational force, because those forces are acting on the actual mass. And then velocity, we just use your velocity update formula to update it, and our position update formula as well. And then here we just repeat the beginning stuff to update our spring force each interval, each delta t. Down here we just repeat all of our energy changes as well to update our energy changes. This is our video of the computational model. All right. Possible error. Hold up. All right, possible error includes the tracker app because it's pretty inconsistent. Also, we only had an X measurement. We didn't have we only had a Y measurement. We didn't have an X. Also, some of the energy may be transferred via heat or energy or air resistance. And also, we're not sure of the strength of the spring because in the real world, springs can be damaged if they're stretched out, or yeah, so they have less resistance. Questions: what does it mean for your model system? Is the energy principle satisfied? Yeah, if we go back halfway through the video, you can see that it is satisfied. Like as gravitational goes up, the spring force goes up down, and vice versa, and the same for delta k. So it does stay constant throughout. What if using the data? So basically, compare our periods via x position and then via y. They are different. You can see the x one is a bit bigger. I'm not sure why, but it's kind of strange. Maybe it's part of error as well. That's it. Thanks. Have a great day.